Thank you for the opportunity to speak today. My name is Tamaryn Menneer. I'm a Senior Research Fellow based in the Environment and Sustainability Institute and also the European Centre for Environment and Human Health at the University of Exeter at the Cornwall campus in the UK. So I'm going to be talking about modelling mould growth using relative humidity and temperature data from inside people's homes. So to give a bit of background, the data come from a project called SmartLine, which was the first project of its kind that we're aware of, running from 2017 to 2023, with a broad purpose looking at all sorts of data to help us understand how we might have healthier and happier lives and homes. The project took place in Cornwall. So this is a map of the United Kingdom with Cornwall marked in black. This is a zoom in on Cornwall, and then this is the study area with Camborne, Poole, Ulugan and Medreath, the towns where the homes were, which together make the largest conurbation in Cornwall, which is typically a rural area. The project was funded by the EU Regional Development Fund and the UK Government, Cornwall Council and the South West Academic Health Science Network. Our main partner was Coastline Housing, who are a social housing provider in Cornwall, which manages the homes that participated in SmartLine. So just to give some context, social or public housing in the UK and around the world is generally subsidised or managed in such a way in order to provide lower rent for people on low incomes who wouldn't necessarily be able to afford private rent or to buy their own home. This situation is also unfortunately often associated with inequalities in health and education and services. So on SmartLine there were more than 300 participants and they answered our surveys and had sensors installed in their homes. From the survey data conducted in 2017, almost all of our participants reported as being white, with 2/3 being female. The average age was 56 at the time of the survey. Much of Cornwall has some of the most deprived or underserved areas in England, not just in terms of income and employment stability, but also health, crime and housing services. And our SmartLine community areas also reflect that. 1/5 of participants did not have an internet connection at home when we started the project in 2017, and the time reported to normally be spent inside the home was an average of 19.5 hours a day. We had sensors in 280 of the homes, which were installed again in 2017. They took readings every 3 to 30 minutes. Each home we had measures of air temperature, relative humidity in the living room and in the bedroom, and air quality in the living room. We also had external environmental sensors outside some of the homes, and we measured utilities, electricity, gas and water in some of the homes. So we collected altogether 700 million data points from these sensors. And this sensor data set is freely available via the UK Data Service if anyone's interested in using that. So going back to the focus on mould, in the SmartLine survey, we asked people, does your home have visible mould patches? And has your home suffered from a mouldy or musty odour in the last 12 months? 44% said yes for mould and 18% said yes for a mouldy odour. These rates are higher than the UK rates. From a survey that was had over 3,000 people respond, we had 24% of people saying yes, they had mould, and 13% having a mouldy odour across the UK. So Cornwall, as you saw on the map earlier, is surrounded by sea on the 3 sides. And compared to much of the rest of the UK, it's got a relatively mild winters and cooler summers, but with higher rainfall and humidity. So we use the relative humidity and temperature sensor readings to investigate mould growth. So here's an example plot of relative humidity in red and temperature in blue from one home over 1 year. And I'll explain what the black line means in a minute. As we've heard from the previous speaker, thank you, there is an existing model of mold growth called the VTT model developed by Hooker and Viitanen, and that model takes relative humidity and temperature data and calculates a mold index. So it was developed in the lab under highly controlled conditions using mold growth on wood surfaces. That's the original, the way the model was originally developed. So first of all, it calculates a critical relative humidity level based on the temperature, so the T value in this top equation, which gives rise to this plot showing that the critical level of relative humidity above which mold grows increases as the temperature is cooler, but typically a critical level of 80% is used in the model. If the current relative humidity is above this critical level, typically above 80%, then the mold growth can grow according to this equation, which takes in the temperature, T, relative humidity, RH, and W and SQ in this equation are the wood type and the surface quality. We didn't have that information, so we set those parameters to 0 in our use of the model. If the current relative humidity is below the critical level, then the mold index can decline. And for wood surfaces, that depends on the length of time that the relative humidity has been below the critical level. So between up to 6 hours below, it declines at the highest rate of 0.032. Between 6 and 24 hours, it doesn't decline. And for more than 24 hours, it declines at half the largest rate. For non-wood surfaces, the top decline rate is used, the highest rate of 0.032. So going back to the plot of relative humidity and temperature data, we can understand what the model does. So the black line is the critical relative humidity level based on the temperature at which mold starts to grow. And we can see that the relative humidity sometimes goes above this critical level, especially in the middle of the plot. And here's the corresponding output from the VTT model for those data. The blue line shows the changes in the mold index at each time step, but adding all of those together, they produce the red line, which shows the mold index increases at the middle of the plot where the relative humidity went above the critical level, and then declining again when the relative humidity went below the critical level. So this model, as I said, was developed in highly controlled laboratory conditions using precise measurements of relative humidity and temperature from surfaces. So our aim was to adapt the model and test whether it could be used in a more generalized way to identify mold from noisier air readings in a noisy home domestic setting using our SmartLine data. So we took the model and tested different values for these parameters marked in red and all possible combinations of the different values that we selected. So there were 360 models altogether to cover each combination of the different sets of values. And we used readings from the living room for one set of models, and we used sensor readings from the bedroom for a different set of models. So we tested 2 parameter spaces. The first was broader and allowed us to refine the values used in the second parameter space, which I'm going to focus on. But carrying over from that first parameter space, the main finding from that was increasing the sensitivity of the model so that it has a propensity to increase the mold index, gave the best performance. So we used a sensitivity that's double the sensitivity in the original model, and we also use coefficients and the constant in the model equation that also increase that propensity to say that there is mold growth. For this second parameter space, we kind of focused in on the critical relative humidity level ranging from 40% up to 80%, which is the value generally used in the model, in the original model. And we also manipulated the sampling interval, so the timing between the temperature and relative humidity readings, and also the method of decline, whether it was based on wood surfaces or non-wood surfaces. So then we ran all the temperature and relative humidity data through the models, calculated an overall mould index for each home. We took those mould index values to see whether they corresponded to the survey responses about mould. And we used logistic regression to do that. So this heat map shows the p-values for the regression for the survey response about mould. So a paler colour represents a lower p-value or a stronger relationship between the model output and the occupant's survey response. In other words, a paler colour represents a better model. So the values are split by the sampling time of 5 minutes and 60 minutes, the decline rate of wood and non-wood, and then also range from the critical level from 40% to 80%. And the top panel shows the values for data based on sensors in the living room, and the bottom panel shows data from models based on data from the bedroom. So for this survey response about mould, the mould index is more strongly related to the survey responses when the model is based on data from the living room than from the bedroom. There's more paler boxes up on the top than the bottom. And also there were stronger relationships when we used the critical level of 50%, obviously much lower than the 80% used in the original model. So here are the values, the p-values for the survey response about odour. For this survey response, the relationships are generally stronger when using the sensor data from the bedroom rather than the living room, and the strongest relationships occur when the default critical relative humidity is 50 or 70%. Excuse me. So this table shows the accuracy measures for the best performing models that we had out of the different parameter spaces that we used. So accuracy was generally around 70% overall. To calculate the accuracy, we use the regression models to provide yes or no responses from the model mould index values. And then we check the yes or no against the survey responses from the occupants of the homes. So these values are for the performance measures for the models that resulted in the highest accuracy measures for each response for mould and for the odour survey questions. So accuracy here is taking into account the true positive rate, which is when the model said yes and the occupant also said yes, and the true negative rate when the model says no and the occupant also said no. We've got the balanced accuracy, which is simply an average of these two, the true positive and true negative rates, and F1, which is a measure of accuracy of the yes responses of the model. So not just the true positives, but also takes into account the incorrect yes responses, if that makes sense. So the overall takeaway, I suppose, is that we found for both survey responses that the default relative critical relative humidity lowered to 50% gave more accurate performance than the other models. So to bring all of that together, we found that the lab-based VTT model can be adapted to identify mould in noisier home settings using readings from the air rather than controlled surfaces. The model improved when we used parameter values that made it more sensitive to identifying mould. So it improved when we increased the sensitivity and also increased the sensitivity by decreasing the critical relative humidity level from 80 in the original model to 50% for these readings taken from the air. So one reasoning that we had for why that decrease might be needed for air readings rather than surface readings is that it seems likely that 80% relative humidity would not be sustainable within a domestic air setting. Typically, 80% is sustainable on the surface, so you might get water pooling or condensation or water leak, but it seems less likely that that would be sustained into the air of the room as well. So by lowering that critical level allows mould to be identified, even if the relative humidity in the air is lower than that on the surface on which the mould is actually growing. Identification of mould was more successful using sensor data from the living room than from the bedroom, while identification of the mouldy odour was more successful from using data from the bedroom. So it seems likely that the bedroom would have less air circulation than the living room because of the movement of people would be higher in the living room. And the bedroom may contain larger pieces of furniture such as the wardrobe and the bed, which can prevent air circulating near the walls and carpets. So less air circulation would maintain the mould favourable conditions within the fabric of the room and thereby leading to high levels of contamination that are typically associated with a mouldy odour. Sorry, excuse me. So we did look at the variances in the data between the living room and the bedroom, but we didn't find that the variances were any more in the living room than the bedroom. But the survey responses about specific rooms did show more contamination in the bedroom than in the living room. Apologies. So more generally, our findings help these kinds of sensors add value to the sensor data. So not just telling us about humidity, but also about mould in these domestic settings. We purposely used a dynamic model, one that uses moment-to-moment time series data. So it inherently builds changes over time. So in future, a model such as this could apply targeted smart control using the dynamic nature of the model to dynamically adapt ventilation before the mould index reaches the level associated with visible mould. So it's not just a case of switching on a fan when the relative humidity is too high, but making the minimal intervention that's needed to reduce mould growth. Here's the publication on the mould model if you'd like to read it further. It's freely available. And thanks to my co-authors and my previous funders and my current funder, NIHR. And thank you very much for listening.